other big geological features in the area. So Jezero Crater is on the inside rim of one of the largest, oldest impact basins on Mars, and that's the Isidis impact basin. And we think that the Isidis impact basin formed about 3.9 billion years ago. So these are old rocks here. And this is one of the major impacts that we think happened on Mars. But not too far away from Jezero and Isidis is Syrtis Major, which is one of the major volcanic centers on Mars. And so Jezero Crater has this unique position, being very close to major impact related terrain on Mars, but also close to a major volcanic center. And if we go to the next slide, what is particularly special about Jezero, in addition to this general setting, is the presence of a delta within the crater. And we think that Jezero Crater was once the site of an ancient lake basin. And there are a number of places on Mars that we think might once have hosted ancient lakes. But what's really special about Jezero Crater is that it's a slam dunk. We have not only the delta that we see, and we recognize landforms like the Jezero Delta here on Earth and deltas that we have here, but in this crater, we have an inlet valley, which tells us that water flowed into the crater. But what is unique about Jezero is that it also has an outlet valley, and we don't always see that in craters on Mars. So we know that this crater once filled up basically like a bathtub to the point where it overflowed out the outlet valley. And so that's really important for us as we're thinking about what a good landing site might be, because not only do we have evidence in the rocks in the delta that a lake was there, but we know that there was enough water there for a significant amount of time to basically fill this crater and then overflow it. And sometimes we think in different places on Mars that water might have been a kind of figurative flash in the pan. But here in Jezero, we know that that water was around long enough to fill the basin. And we think that might have been a great place for life to exist and take hold. And we have the types of rocks, similar to rocks here on Earth, that are very good at preserving that evidence of life. And deltas here on Earth are great places to go to look for organics. And we hope that the same is true here in the Jezero Delta. If you advance to the next slide, I'll just point out that the other thing that's really unique about this location, and what you're seeing here is a false color image from one of our orbiter spectrometers. So this is an instrument that tells us about mineralogy. And the colors highlight the fact that there's a lot of mineralogical or compositional diversity here in Jezero Crater. And what you see here in green, those rocks there on the inner margin of the crater, those rocks contain carbonate. And when you think about carbonate, you might think of reefs in the Bahamas or in Australia. And honestly, that's kind of what we think about too. We don't know that that's what we have here, but we have carbonate rocks in what was perhaps a shallow lake environment. And that's a great place for both hosting life and preserving life. And so we're really excited about Jezero Crater for a number of reasons. We know it had water for a significant amount of time. It has the rocks that are really good at preserving evidence for life. And we have a number of very interesting and unique geological and astrobiological targets here in this location. And another special thing about deltas is that they're really good at concentrating and collecting rocks from a large area into one place. And so that delta right there represents, sediment grains in that delta came from very, very far away outside the crater. So by going to this one location in the crater, we can sample locations far, far away that we might otherwise never have been able to go with the rover. So deltas are really good at concentrating a geological story in one place. And so these are some of the reasons why we've been so excited about Jezero Crater and the potential for exploring this with the Perseverance rover and helping us understand the surface of Mars and Mars's potential for hosting ancient life.
Wow, this is great. So I think a lot of us know landing on Mars is really difficult. And so, Neil, I want to ask you about why is it so difficult to land on Mars? And then can you tell us about the aeroshell and the heat shield and how that's used to protect the rover during the landing?
You could go to chart 10 for me. Thank you. Okay, so entry, descent, and landing is a very complex process. There's lots of things that have to go right in order to get down to the surface. And that's one of the things that makes it so difficult. And there's been a lot of failures at Mars. Fortunately, JPL's been very lucky at getting most of their spacecraft to Mars, but some of the other countries that have tried have not been quite so lucky. Just to give you an idea of the complexity, the spacecraft essentially takes 6 to 8 months to get to Mars before it's ready for the entry phase of the mission. And the first thing that you have to do is separate the crew stage from the aeroshell. And so now the aeroshell is floating on its own, heading towards the atmosphere. It does have thrusters to adjust the angle of the spacecraft, of the aeroshell as it hits the atmosphere. Since it was previously installed on the cruise stage, we do have to adjust the center of gravity of the aeroshell before it hits the atmosphere. And we do that by deploying a bunch of very heavy tungsten masses. There are actually 2 tungsten masses, weigh about 164 pounds each. And that sets the gravity where it needs to be as it hits the atmosphere. The spacecraft is really on its own at this point. Everything is robotically controlled and pre-programmed, which means you have to do it right the first time. There's no joysticking this spacecraft as it comes in. So as you hit the atmosphere, the aeroshell is the primary protection for the rover that's inside it. There's a peak heating phase where the heat shield gets to about 3,500 degrees surface temperature on the outer surface. And that aeroshell protects the rover from seeing those high temperatures. There's a thermal protection system called PICA that protects the rover by ablation. It allows the heat to flow away from the spacecraft, and the back shell also does some protection there. But once you get through that peak heating, now you're just kind of coasting. There's some additional balance masses that are released. 65-pound masses are ejected from the aeroshell. And that allows us to kind of surf our way through the atmosphere to the final landing point. And so it's actually, very ingenious. There's lots of things going on during EDL. All of these have to happen just right. The next major event would be to deploy the parachute. Parachutes seen a lot of testing. We're very confident in this parachute. JPL did all the testing, but there's always things that can go wrong with parachutes. And then after you've coasted on the parachute for a little while, then the heat shield is released from the rest of the structure. And there's some very good videos on YouTube showing the MSL heat shield leaving the back shell. And that allows the radar to turn on at the right time to see how far above the ground you are and determine the final landing points. There's lots of cameras on board that are used to optically navigate the spacecraft to a safe landing zone. The sky crane was developed by JPL to allow various separation hardware to fire and lower the rover down to the surface so that it can fly away. So all of this has to happen in 7 minutes. So anytime one of these happens, it's just very exciting. There's lots happening and lots that has to go right. So as soon as you hear that, the word that you've touched down safely, there's a lot of cheering that goes on.
Oh, that's wonderful. 7 minutes of terror. I can only imagine.
I had some questions about the back heat shield.
Yeah.
I do have a picture on slide 11 showing you the heat shield. So this is the picture of the heat shield with the TPS ablator installed. We use a material called phenolic impregnated carbon ablator. It's actually a carbon weave that gets impregnated with phenolic. Phenolic is what ablates off that surface and allows the surface to stay cool enough that it doesn't soak back into the rest of the spacecraft. The next slide, you can see the overall aeroshell. Slide 12, please. So here's some additional hardware that's on board this aeroshell, in addition to, and most of it is mechanisms. I talked about the balanced mass devices that are ejected. That was all part of the aeroshell mechanism. There's also 9 separation fittings that are fired in sequences of 3. That is all hardware that was built at Lockheed Martin and had to be tested. There's a Medley 2, which stands for Mars EDL Instrumentation 2. MSL also had that hardware, and it measures things like temperature of the surface, the amount of ablation that's occurring, the pressure on that front surface of the heat shield. All of that hardware is installed and will be active during the EDL event, so we get information for future missions. The back shell also has a ablator product on it. It's called SLA 561B. It's the same material that was flown back on the Viking program. So a lot of this technology has been used in the past. The structure itself is almost totally M55J composite materials. It has to be very, very stiff to withstand the high pressure of entry. There's 2.5 inch thick honeycomb on the heat shield structure that adds to that stiffness. So it's seems very simple, but it's a very complex piece of hardware. So.
That it is, and it's got to withstand those extreme environments. So thank you so much for building that. So I'm seeing some questions about if there's aero braking and a little bit more on the entry, descent, and landing. And so, George, can you talk a little bit about the sky crane that Neil mentioned, and why is that the suited landing mechanism versus other landing systems?
If you're familiar with how the Curiosity rover landed, then to the untrained, well, it looks very similar, right? But there's actually a lot extra going on for Mars 2020 and Perseverance that you can't actually see. A lot of improvements, and part of that starts with the sky crane and the descent stage. And there's 2 key new capabilities that we're going to have for Mars 2020 that Curiosity didn't have. One is called range trigger, and the other is terrain relative navigation. Range trigger is all about when do you pop the parachute. Previous missions would be able to, as they're coming in to landing, they've got an estimated velocity and estimated distance of the surface, and they determined on when to pop the parachute based on their velocity, a certain velocity marker. We were able, by just changing one line of code in the system and using other measurements in terms of our range to the target, we're able now to pop our parachute based on our actual estimated range to where we're going. What that helped us do was shrink the size of what we call the error ellipse, or the landing ellipse. So where Curiosity was shooting for a target, ellipse that was 20 by 25 kilometers, we've been able to shrink ours down to about 8 kilometers diameter circle. So was really what enabled that, and then terrain relative navigation enabled us to choose Jezero Crater, because it helps us get to more interesting landing sites that the scientists want to get to. Terrain relative navigation is very similar to how some of that is done here on Earth in different systems, but we have a downlook camera that's on the bottom of the rover, and as we're coming down with the descent stage, we're taking pictures. And the rover is comparing the images it's seeing to an onboard map that it's carried. This map was generated from the orbiters that we have around Mars, and the same ones that we use to pick the landing site. And on that map, we've marked out where are maybe some of the more dangerous places. And if, as the rover, as it's coming down, it can compare where it's headed with that hazard map. And if it looks like it's going towards one of those hazards, we have a built-in capability. It's called the divert maneuver. Curiosity did this too. After we pull away from the back shell and the parachute, we don't want that falling on top of us when we land. So we had a built-in divert maneuver. We used those engines to just go off in a direction. Curiosity, it wasn't a guided thing or a decision. It was just go in a particular direction. For us, we're able to use that same divert maneuver, and if it looks like we're headed to a more hazardous location, use that to go towards a safer location. So those are the two big new things that we have going on with our descent and landing. And definitely for those of our viewers, if you haven't seen it, I recommend searching for either 7 Minutes of Terror or Curiosity Landing. Watch the animated video that animations of the landing, but it's coupled with the team as that is actually happening with Curiosity landed. It's very exciting because you're going from, once you hit the top of the atmosphere, you're going about 13,000 miles an hour. You're hypersonic. And then when you pull that chute, that's a supersonic parachute, that slows you down to about 1,000 miles per hour. Then you slow down using the descent stage, getting down to 200 miles an hour. And finally, we're only going about 1 meter a second, or 1 mile, a little over 1 mile an hour, when we gently set down that rover on the surface.
That's amazing. And I'd be remiss if I didn't mention the Aerojet Rocketdyne thrusters being used on the Sky Crane to lower it down.
And thank you. Thank you for providing those.
You're welcome. I'm just going to highlight the propulsion throughout the mission. So now that we've safely landed on Mars, Katie, let's talk about the science. And you already talked a little bit about how you remotely operate, but what's your first thing you're going to do once we safely land on Mars?
Well, we're all going to heave a big sigh of relief and then let out a major cheer. But then, we get down to business. And George mentioned the terrain relative navigation. And I just wanted to mention that, that capability and the enhanced computer that allows Perseverance and Mars 2020 to do that terrain relative navigation is actually, we're taking advantage of that on the surface as well. And so we're using that faster, better computer processing to actually be able to traverse autonomously in a way that previous rovers have not been able to. So we think we can cover more ground every day with Perseverance than perhaps Curiosity ever was able to do, because we're basically with the rover surveying our landing site as we, our terrain in front of us as we drive, and the computer is making decisions about where to drive. And so that's an exciting new capability that we have thanks to this better processing power that is also benefiting our entry, descent, and landing. But if we think about what we're doing on the surface, so we'll have hopefully our science mission plan in mind. So the minute we find out where we've landed, that'll all kick into high gear. So we'll think, okay, where did we land in this site? What do we want to do here at this location? And where are we headed next? Of course, during the early days of the mission, we're doing a series of instrument checkouts and checking to make sure that our systems are operating nominally, and we come online piecemeal. So slowly we add capabilities every day. So the science team during this period of time is really focused on coming up with that science plan. And as we test out our instruments, we'll be selecting targets. And this is something that we do on other rovers. And we say, okay, well, we have this much time today. And we're using this instrument. Let's identify the most compelling scientific targets, and we put a plan together. And of course, there's lots of deliberation that happens while we do that. The scientists talk about what is most scientifically compelling, and then we talk to the engineers. And sometimes the engineers will say, sorry, can't do that, it's too dangerous, or we can't reach it. And then we have to go back in conference and say, okay, well, maybe we'll change our plan, or nope, we really want this rock, can you get it for us? And so that kind of back and forth is one of the things that makes working on a rover mission so fun, I think, for so many people, is this working together as a team and doing that back and forth and give and take as you take hundreds of people to operate a single robot on another planet. And so it's a really unique experience that we have, and one that is very satisfying every day when you can come to a consensus about what to do on the surface, and then actually you get that data back. And so we'll be focused on that, getting through those early days of Mars time when we're living on the Martian clock instead of the Earth clock. And those are fun, but kind of stressful days when you're walking around like a zombie sometimes because you're sleepy. But we do our best to make good decisions for the rover during that time, and that time is really essential to take full advantage of all the time that the rover has awake on the surface of Mars before we take our own human considerations back into account. So eventually we will transition off of Mars time. But then during that time, that's when we are getting excited for our first sampling opportunity. We have ambitious sampling goals with this mission, and so we know that we have to get going putting together that sample cache, because we hope that we have a rendezvous a couple years down the line with the next leg of Mars sample return. So we've got to get going, and we've got to do the science and collect the samples that will enable the next leg of that campaign. So we'll be thinking about that as soon as we get on the surface and doing our best to plot a course and collect a suite of samples that will really feed, I think, generations of scientists when those samples come back. So we feel the responsibility, but we're excited to have that responsibility, knowing the potential for what it sets up in the future.
Oh, that's wonderful. So I know we're at the top of the hour. The panelists have agreed that they can stay longer, but and so we're going to talk a little bit about future Mars exploration, and then we'll get to more Q&A from the audience. But I just want to let folks know who did have somewhere to go that the panelists are going to stay. So let's move in. You mentioned the sampling. So Perseverance is collecting samples. So Neil, Lockheed's been a part of some previous sample return missions. And so can you talk a little bit about sample return missions and how you possibly could return samples from the Mars Perseverance rover?
Sure. So there's already RFIs in place for this next mission that you're talking about. It's going to be called Mars Sample Return. We recently completed a proposal for one of these RFIs to go off and build another aeroshell. This one, Mars 2020 aeroshell, was 4.5 meters in diameter. The next aeroshell for Mars Sample Return is going to be even bigger, believe it or not. It could be as big as 5 meters in diameter. So we were asked to propose this newer, bigger aeroshell. In addition, there's a new lander that's an even larger lander that's JPL will be responsible for. It's called the Sample Retriever Lander. And so this big lander has to get down to the surface, and its primary purpose is to go pick up the samples that Perseverance has left down on the surface. So the next mission to Mars will be close to where Perseverance is right now so that they can go pick up those samples. And then there will be additional missions that actually land a rocket down on the surface of Mars that could be used to take those tubes, stainless steel tubes that have samples from Perseverance, and fly those back to the US or back to the world, the Earth, so that we can see what's actually down there on Mars and see if there's any signs of life. But those are missions out in the future. This particular RFI we just proposed to would launch in 2026. So we're talking about 4 or 5 years out. And then at the sample return mission is probably a year or two after that. So
Great.
we're hoping to be part of all those. We love Mars, and we love going there whenever we have an opportunity.
We have that in common with Aerojet Rocketdyne. We love Mars too. So going to turn to George and just see, George, do you have any other additional thoughts on sample return missions? And then if not, what kind of planning is going on for future Mars robotic science missions?
Since Neil brought up the fact that there will be future missions that will need to go return these samples. We, Mars 2020, cannot lift off and come back home. And one thing that's very unique, I talked about the prior missions, and we kept building on prior missions and the knowledge. Each mission we've done has, taken the knowledge from prior ones and built on that. But this will be one of the first time where we've actually had hardware interfacing between two different missions launching in two very different opportunities. And so I want to illustrate kind of what that interface will be. So since I'm at home, I didn't have my usual props of my 3D printed sample tubes, but I realized that a little flashlight is about the same size as a sample tube. I even took my calipers to it, and it just so happens that this is roughly the same size and shape, even this little bulbous end of a sample tube. So we're carrying about 42 of these with us, and we'll be able to leave them on the surface. And so the future missions that we're talking about designing, we've already been working for the past several years creating what we call interface control documents. So basically agreements between our mission and future missions to be on, are there any requirements we have to actually place on these tubes, and how we can keep the samples, keep sample integrity for when we eventually get them home. And what do those future missions, how do they need to be designed to actually pick these things up and put them in some sort of container to come home? And continuing our flashlight analogy, the actual sample itself, it turns out it's pretty close to the size of a AA battery, maybe one and a half AA batteries. And so that's what we're talking about. This is going to be the goal that we get home. And if you can go to chart number 21, I actually have a picture of the real sample tube. This is part of our caching system. This is during thermal vacuum testing of it. And what we're doing in this image, what is happening, we're testing, putting the tubes in and out of their storage silos that we have to carry. We're able to, once the sample is in the tube, we have to bring it inside the rover, seal it up with a hermetic seal, a cap, and then we have two choices. We can either hang on to it for a bit and wait until we want to drop it, or we could drop it right there. Most likely our plan is we're going to be putting them back in the silos where we pull them out. And then once we get to a location on the surface where we want to place this set of samples to await the future missions, then we would start depositing them there. We call that the depot cache approach. So all these future missions that we're starting to look at is we're in the planning stages now. And a big component of that is doing it with our partners in the European Space Agency. So some of the elements that Neil talked about, the retrieval landing system, landing a rocket, we call it the Mars Ascent Vehicle, that would lift off this set of samples, would be provided by, we're looking for being provided by NASA. European Space Agency is interested in providing what we call the fetch rover, such that if Perseverance itself isn't able to deliver the samples to that lander, a fetch rover, a smaller thing that's specially designed to go and pick up these types of tubes and bring it back to the Mars Ascent Vehicle. And then once it gets off the surface, there needs to be a return orbiter. And that's the third component of this, sort of three major components: the sampling mission, that's us; a retrieval mission on the surface to get it off into Martian orbit; and then another mission that will rendezvous with that sample container that's in orbit around Mars and bring it home to Earth.
Wow, that's amazing. Thank you so much for sharing that and bringing your flashlight to explain it to us.
Oh, I got a new prop now. It's great.
Great. All right. So, Katie, as I mentioned earlier, I've got this great exploration rocket NASA does. It's the Space Launch System that wants to bring humans to Mars. So from your perspective, the science perspective, what needs to happen before humans go to Mars?
I think going to Mars is kind of like planning a trip here on Earth. You don't go without having done a little bit of research about what the location is like and what the conditions are like, and perhaps what you need to bring with you and what you can get when you're there. And so, in some ways, it's very similar to planning trips here. But in particular, we want to understand what kind of conditions our astronauts or Marstronauts would experience if they went to the surface of Mars. And we've been making progress on that question with previous missions as well. And in particular, one of the concerns that we have for astronauts when they're out in that space environment is radiation. And there's an instrument on the Curiosity rover called RAD, which has been measuring radiation since it was on its journey to Mars. And so we know a lot about from previous rovers. But with Perseverance, we have a weather station basically to understand pressure, temperature, humidity, dust in the atmosphere. And those are all very important pieces of information we would want to know if we were to send astronauts to Mars, to know what kind of environment they would be encountering and what kind of equipment they would need, how their spacesuits need to be built. And so our robotic explorers are doing some of that reconnaissance and data collection that can help enable planning for human exploration. Another thing we often think about is the in situ resources that Mars might have that astronauts could take advantage of when they're on the surface and perhaps don't have to bring with them, because mass equals dollars in a lot of in a sense when it comes to missions like this. And so if there are ways we can take advantage of the resources that Mars has, we don't have to bring those things with us. So we think about things like understanding the climate cycle and understanding water and where it is at the surface or subsurface, and ice and what conditions, what the weather's like, to affect things like where those resources might be. And so those are the kinds of things that we think about and we want to understand, and what the material properties are of even the soils and the rocks are on Mars, because those could all be different resources that get used by astronauts in situ on Mars. So I think those are some of the things that we think about, and that Perseverance in particular can contribute towards. And so each time we send a robotic explorer, we're making progress towards that goal of sending humans to Mars. And we can do that, fortunately, in a way that addresses interesting science questions for Mars about Mars's atmosphere today and the conditions on Mars, while also, in service to that goal of human exploration and advancing that part of our objective.
I love the sustainable approach that you all are really taking to exploration and taking it one step at a time. I think it's great, and I commend you for that. So before we get into the lightning round of questions, because we've got a lot coming at us, I wanted to ask Neil one thing about, he mentioned the Dragonfly that he's working on, which is going to send like a drone-like vehicle to Saturn's Titan moon. And so I wanted to know if you could talk about the lessons learned from the Mars 2020 Perseverance rover and the Mars 2020 program, and how you're applying that to the Dragonfly mission, Neil.
Sure. So we're always gathering lessons learned from the various programs that we work on. Started back, at least for these big Mars missions like MSL, Mars Science Laboratory, we had to build a very similar structure, identical structure, essentially, is considered to be build to print. So back on the MSL program, we actually built 2 heat shields instead of just one. We needed a second heat shield to do environments on, and that heat shield became a spare, which when we got on contract for Mars 2020, that piece of hardware was provided as government furnished equipment for us to save money on the Mars 2020 program and use that heat shield in addition to the new back shell that we had to build. Well, as it turns out, the biggest risk on the program for the aeroshell was that heat shield that was now 10 years old survived the static test. It had to go through testing just like any other piece of flight hardware to prove that it was capable of going to Mars again. And as it turns out, that heat shield was not adequately built to survive the new environment that was being imposed on it by Mars 2020. And we had a failure at that point. So we had to go back and figure out, well, what happened to that first heat shield? It was the first heat shield of its kind of that size. So we learned a lot. We figured out what went wrong with that first heat shield, and we fixed it for Mars 2020. So it's all information that will be used on this new mission called Dragonfly. Turns out Dragonfly wants a 4.5 meter aeroshell as well. So it's very applicable to use everything we learned on Mars 2020 and MSL on this new heat shield. We learned a lot about how to improve our processes, how to test the hardware early so you know that there's no issues with the hardware. We developed some new test approaches using IR thermography to look for disbonds of the structure. We did some testing by applying a film to the surface of the heat shield during the static test so we can monitor strain levels as you're applying more and more load to that structure. So that we've got tons of lessons learned. We've got a big long list. I've got the same people working on Dragonfly that worked on Mars 2020. So
that's wonderful.
Yeah.
All right, so we're going to go into lightning round where we're going to try to ask as many questions as we can and answer them as quickly as we can. So Christopher asked, what's the launch system? So I'm going to go ahead and answer that one for you. It's ULA's Atlas V rocket. Ashley wants to know, you said it uses nuclear power. Is that the type that converts nuclear directly to electricity? George, do you want to take that one?
Yeah, we use what's called a radioisotope thermoelectric generator, and we use the exact same type that MSL used. And the basic technology has been used for U.S. space missions for decades, for 50 years. And in fact, Dragonfly will use a similar system. And what it does is you have a small pellets of radioactive material, plutonium dioxide. It's a ceramic material that just heat. And we have several of those stacked up, and we have thermocouples wrapped around it. So it's a passive system. There's no moving parts. And those thermocouples directly convert that natural heat from radioactive decay into electricity. And for Perseverance, we get actually a twofer with the system. We don't, in addition to the electrical power, we also get the heat, which is what we need on the surface of Mars. So there is actually a fluid loop pumping through the rover to help transfer some of the waste heat from the RTG into the interior, what we call the warm electronics box, to keep the insides of Perseverance nice and warm. And that's what enables us to do what we need to do on the surface of Mars.
Awesome. And I'll also mention Aerojet Rocketdyne builds the nuclear power source for
That's right, you do.
The rover. So another Ashley wants to know, how long does it take to build a rocket? I think that's going to probably be best answered by the rocket provider, ULA, United Launch Alliance. So since we don't have them on this panel, I recommend if you go to their Twitter account and tweet them, I think it's at ULA Launch, they probably will answer that question for you. So next question from Joel. What opportunities might there be for citizen scientists to participate in the mission? Katie, is that something you want to tackle for us?
Yeah, you know, we've thought about different opportunities, and there are some opportunities already to do Mars research and assist with Mars research. And so citizen science, I think, is a growing area. We don't have anything at the moment that we have planned, but we're thinking about it in terms of thinking about identifying interesting places in the landing ellipse and perhaps, you know, opening that up and allowing, you know, our own community to take a look at the landing site and dig into the images and perhaps help us identify interesting locations. So we don't have anything that I can say that we've confirmed that we're going to do, but we're thinking about it, and we'll be sure to let you all know if we are able to kick something off like that. That's a great idea.
That's awesome. All right, so next question, George, this might be one for you, for Mario. Why are the wheels covered?
Oh, from the picture. Actually, if you can put one of those pictures of the rover with the wheel coverings. One of the, we're searching for potential evidence of ancient Martian life, right? Well, the first thing you don't want to do is bring some sort of Earth life with you and have our science instruments basically detecting Earth life. So one of the key things all Mars missions have done, this is part of what we call planetary protection, is, and that's why when you see these spacecraft being put together, they're in clean rooms to keep any potential of Earth contaminants as few as possible off the rover. So since the wheels themselves are what's going to be touching the surface of Mars, we want to keep them as clean as possible right up to the last minute. Katie, is there anything else you want to add to that, or did I hit it?
No, I think you hit it. I mean, we take it very seriously, the cleanliness of the rover and the system, because we want to make sure that the samples we get back, and the things that we find in those samples are indigenous to Mars and not things we've brought with us. And so we take that very seriously for this mission, particularly because of the sample return component. And so we've taken extra measures to keep the spacecraft clean and to protect what we call the sample intimate hardware, the parts of the rover that are going to interact directly with the samples. And so the wheel coverings are one example of ways that we try to keep the rover and the spacecraft clean as we're putting it all together and getting it ready for launch.
So the tires are a big question. So Patrick wants to know, how are the tires different on Perseverance opposed to Curiosity?
I can take that. So as some of you may have noticed, Curiosity is starting to get some holes in its tires. And this was not completely expected. And we, of course, we're doing a lot of things very heritage, trying to do as much build to print as we can. But even though the wheels are still, even though the part of the wheels have some holes in them, they're still perfectly capable and functioning. Curiosity can keep doing its mission for a long time. But we certainly thought that we'd like to maybe make some improvements. So what we did the test with various different types of sizes, size modifications to the wheels, also changes to the treads, because actually the tread shape on Curiosity is sort of a jagged chevron pattern. Turns out that actually is part of what was contributing to some of the holes. As we would roll across a particular rock, it would create greater forces there than it was designed. Oh yeah, thank you for putting that up. You can see on the Curiosity wheel that jagged, what we call the grouser. So for Perseverance, what we've done is we made the skin, oh, perfect. You'll see the skin of the wheel, it's still all the same material. It's all hogged out of a single chunk of aluminum, but it's slightly thicker, so it's more robust. But once you do that, you're adding weight, right? So how can you potentially offset that? So we made the wheels slightly narrower. We also made them slightly larger in diameter, and then we changed the tread pattern there. We now have sort of a curvy wave sign. And it turns out that these wheels are actually much more robust. We have a place, a test setup at the Mars yard at Jet Propulsion Lab, where we've run these wheels around and around and around, tens and tens and tens of kilometers, and they are just scuffed. So they're going to be quite durable for us. And on top of that, the new grousers actually give us a little bit better traction, so that we have a little bit more margin and a little bit more robust capability for going up or down slopes and sandy terrain.
Oh, that's awesome. All right, so we're going to move on to our next question. How, if at all, is COVID-19 threatening the July launch? And this is coming from Julie. And then what preparation activities, if any, have been moved to a virtual environment?
I addressed that a little bit earlier, but I'll repeat. Certainly the COVID-19 situation, like many people around the world, had to adjust to the way we do work, particularly for our folks who are doing the mission critical work. The majority of our team has successfully transitioned to remote teleworking. Timing helped in this regard. Most of our hardware was completed and already at the Cape, and had already been transported there. So with the small teams that we still do need to have working on the hands-on critical hardware, like I said, we've kept the first priority is the safety of the team, as well as the community they're in. So we've been able to work with occupational health officials at our NASA centers and taking guidance from Centers for Disease Control, as well as the local centers there at Jet Propulsion Lab in Kennedy, and been able to put in place practices so that our team can operate safely. And so far, we've been very successful. We are still on target for launch, so still making the milestones.
Awesome. Sunny wants to know, Katie, will Perseverance provide data to students, community, or universities for research?
Yeah, so all of the rover data goes out almost as soon as it gets back, and we have agreements to make sure that the rover data that we collect is available and accessible by the public. And so, for instance, the images that the rover takes, those are, again, available almost immediately once they come down. In terms of some of the other data sets that we have, usually they take a little bit of processing and preparation, but then they get posted, particularly on the, it's the PDS is what it's called. It's a data repository, and we have an agreement to post the data there to the PDS. It's usually about kind of a 3 to 6 month time frame from the time that we get it. It's packaged with the proper files and explanation and put on the PDS, this data repository. And so yes, we make that data available to the public, and we encourage and are excited for those outside of the rover team to dig into that data and present science results and interpretations from that data.
Awesome. All right, I know we have just a little bit of time left. So Saita wants to know, should NASA collaborate with other international space agencies for Mars exploration like it does with the International Space Station?
I'll take that one. We absolutely do. In the game of space, we all can accomplish more if we're working together. Perseverance itself certainly has international contributions. If you can go to which one? There's the chart of the rover showing the instruments. Yeah, you'll see there's a couple of flags here. We have several contributions.